Okay, so thanks a lot. It's a great honor to be talking in this meeting, which honoring Raghu. So the talk, the talk is another formula. so the thing about the formulas, whether you like it or not, essentially everything we know about one-dimensional diffusive driven systems, their fluctuations, is from exact formulas. Integrability. This formula, what I'm going to talk about today is a little bit different. You know, one of the things about integrability, I mean, you saw yesterday in Alejandro's talk, the integrable polymer is this log gamma polymer, right? And okay, whoever heard before that about the log gamma distribution, right? You might want to think, maybe it would be better to have a Gaussian polymer, right? Why isn't that one the integrable one? And you know, the KPZ equation itself is the ultimate Gaussian polymer. It's a Brownian motion weighted by running through a white noise. So everything's Gaussian. And somehow you think you can exploit that. And that's never really been done. And so what this talks about is what you can milk out of that. Okay? So what I'm going to do is I'm going to show you the formula. And you're all going to go, what? Like, it takes a little while to get used to this formula. And so to get you used to it, I'll show you where it comes from, and then I'll give you some applications. And maybe by the end, after these applications, you'll have some appreciation for the formula. So this is a joint work with Yugu, who's here but not here because he has to teach his class. And some of it's with the postdoc at Toronto, Qianhao Xian. Okay, so the formula. Okay, so here's the KPZ integration by parts formula. And I have to show you all the pieces. So first of all, the KPZ equation. I hope you can see it. I hope it's not too small. So the KPZ equation, I think most of you know. It's being driven by a space-time white noise C. And this bold E is the expectation with respect to this space-time white noise. Sorry about the bracket there. And it's delta correlated in space and time. The derivative of H in space satisfies, well, this essentially equivalent equation called stochastic Burgers. Okay, and you just formally differentiate the equation, and that's the stochastic Burgers equation. Okay, so what we're going to do, we take the solution, and the solution's starting from some U0 for stochastic Burgers or some H0 for the KPZ equation. And we look at the solution at time t, and we hit it with a test function f. Okay, so just think of f as a smooth test function. And that thing's called y. And now you take some f. F, you can think of, it's just, again, another type of test function. Maybe think of it as a polynomial or something like that. Okay, and we'll take the expectation of f of y times y, and that's given by this mess. Okay, so in the mess, there's the L2 norm of the little f, the test function, and then f prime y, and some of this people will appreciate what this is. This looks like Gaussian integration by parts, right? Okay, and then there's some correction term for being KPZ. Okay, so what's the correction term? And I'm going to show you the formula over and over, so don't worry if you don't get it the first time. Okay, so there's some integrations with these with these test functions f. And there's f prime y. And then there's this expectation over polymer measure. So here's the expectation over the polymer measure. Now the polymer measure is the measure on Brownian motion reweighted by going through the white noise field and then picking up this H0 at the end. I will show you on the next slide exactly what it is. Okay? So we have expectation on the polymer measure, and so xt is the polymer path, which is these reweighted Brownian motions. And you see you take your initial U0 and you weight it by the polymer, and here you take two copies of the polymer, and you look at the sign, the sign being the sign function of the difference of the x's. And okay, so that's the formula. And that's the formula. And so the rest of the talk, don't worry if you didn't catch it the first time. The rest of the talk is where does the formula come from, and what are we going to do with it? Okay? Why is this interesting? Okay. So first, where it comes from. So where it comes from, I'm going to sort of sketch the proof. Okay. Okay, so the proof, the proof is mostly a Gaussian integration by parts, but then there's one little twist which is not obvious. Okay, so first, in order to integrate by parts, we'll take the white noise and we'll smooth it in space a little bit. So phi sub epsilon is just a little smoothing bump, okay? It's locally supported and smooth and symmetric. And this thing called C epsilon, so that's just your smoothed out in space white noise. And then, okay, and so it's been rescaled like this. And so now the C epsilon, it has a covariance in space now, which is just the self-convolution of this phi epsilon, okay? And now the polymer measure, okay, the Z, you can think of as dx of log z, or you can just think of log z as the h. These are the smoothed out KPZ, KPZ being forced by this slightly smoothed out noise C epsilon, or the stochastic Burgers forced by the C epsilon, okay? And the z is just an expectation. So now this expectation here, that's the expectation of our Brownian paths, okay, to differentiate from the expectation of the background noise. Okay, so there's a Brownian path, and it runs through this smoothed out white noise field, just like in Feynman cats. And then you have to subtract some self potential to normalize it. And then at the end, it takes this initial H0. H0's derivative is called U0, and it reweights the paths according to their endpoint, okay? So that's the Z, is this object, and the dx of log z is the U. And okay, good. I hope everybody's following. I don't know how complicated it is. Anyway, so the U, now because of this polymer structure of this whole thing, we can just write the U. You can just actually take the derivative in x, right? There's no problem. You just take the derivative in x, you just get the derivative of this guy. The derivative of this guy is just this, okay? Now, this kind of expectation, where there's an expectation with respect to this guy, I'll just call that E poly. That's just, I just call x plus bt under this reweighted measure. That's called the polymer measure. Okay, so the polymer measure is just the reweighted measure according to this, going through e to the integral of c, okay, plus the h0 at the end. Okay, so that's what the polymer measure is. And the polymer measures on the previous page were just the limiting versions of that when epsilon goes to 0. All right, good. Okay, so U can just be written as an expectation against of this stuff against the polymer measure. And now, okay, good. So now we have f of y times y. But remember, y is just the integral of f against u. And so here's u, parts of u, a piece of u. And I'm just going to integrate it by parts. Now, what's integration by parts? Well, you know how to integrate by parts, a Gaussian measure, Gaussian integration by parts. And so you can integrate, there's just the continuum version of that against a Gaussian white noise is just this continuum Gaussian integration by parts. And you just pick up, the Malleman derivative, okay? So this dsy is just the Malleman derivative I got by integrating by parts across there. And the Malleman derivative applies to the f, and it applies to the of course, the derivative, the polymer measure with respect to the, okay? Because this is not, this measure, this polymer measure, of course, it depends on all the noise and all this crazy stuff too, right? Okay, so, and okay, by Leibniz rule, you can expand that. And then there's a little bit magic happens, is that when you differentiate the derivative of the polymer measure, everything just vanished by symmetry after you take expectation. Okay, I won't go into that, but it's a simple thing. It's just because every term you get is just a self-interaction of the polymer with itself, and that just gives you basically the convolution of phi with itself at 0, which is just prime, which is just 0 because of symmetry. That's a space, this just means the space derivative with respect to that variable, yeah. Any other question here? Okay. Good, yeah, so then the only thing you have is just the Malleman derivative of f is just f prime times the Malleman derivative of y, because f is just f of y, and the Malleman derivative of y is just another term involving the same kind of things, and so you put it together and you get an object like this, Okay, I'm skipping some steps here, but you can imagine, right? And so this is where you get this phi epsilon star phi epsilon prime of the difference of two polymer paths. That's because one came from here and one came from this differentiation. And you don't get that when you do this, and that's why every term vanishes. Okay, so this is the interesting term you pick up. Okay, so I hope, I mean, of course, it's complicated to see a proof, but I hope you get some idea of how you pick up this extra term. Okay. Watch. Okay, and so now we want to let epsilon go to 0. Okay, so now the fun start. Okay, so far it's just Gaussian integration by parts. Okay, but there's a twist. Exactly what you said. Okay, so far we have this formula. This is just an encapsulation of what we got so far. There's this other term because I didn't do anything to that guy yet. Okay? Okay, so now what are you going to do with this? It's just going to blow up. As Gerard said, actually, it just goes to the derivative of the delta function. What the heck is that? Oh, yeah, but now you do Ito's formula. OK, so this is the whole trick. Ito's formula, this thing, you just becomes antiderivative of this thing, right, at the two endpoints. OK, these two polymer, they were starting at x2 and x1. And then a term like this, a stochastic integral. And now you let epsilon go to 0 on that side, on this side. Okay? But this guy, of course, he just goes to the sine function, right? Because that's the integral of the, phi star phi. You integrate it, you just get a sine function. Now this guy, here's the whole trick. This guy goes to 0. There's no stochastic integral in the limit. So in the limit, the Ito formula, the stochastic part just poof, goes away. Okay, how can that happen? Okay, so how does it happen? Well, there's two stopping times. This x1 minus x2, these two polymers, they go running until they get into the range of this phi epsilon star phi epsilon, okay? The first time they hit the range, I'll call that sigma, okay? And then they keep going until they hit 0, okay? Now, after they hit 0, there's absolutely nothing that this thing can contribute because the two polymers are interchangeable and this object's anti-symmetric. Okay? So you only have from sigma to tau. From sigma to tau is a hitting time of roughly epsilon to a hitting time of roughly 0. Now you might think, oh, but it takes an infinite amount of time. But no, because you're only counting between epsilon and 0. Once it leaves this little tube between epsilon and 0, you don't count anymore. So it just keeps trying and trying and trying. And actually, it's a finite time. The time is of order epsilon squared, of course, but it has a finite expectation now because it's in a tube. But phi epsilon star phi epsilon is only epsilon minus 1. So the whole thing's order epsilon. And we can prove it up to these log corrections. Okay, this is not the proof, but it's the idea. Okay? And so, of course, it goes to 0. So there's nothing left, and that's our formula. So you see the formula involves this very, very funny special cancellation in Ito's formula. Okay? It's a magic thing. Okay. Any question?
The question I was asking is, does this blow up? In fact, you're saying, no, it's going to 0. None of it doesn't blow up.
It's amazing. Amazing, eh? Amazing. Yeah, there's the boundary terms. Yeah, the boundary term, but they're just finite things. Yeah. Everyone okay with that? All right. Applications. Let's do application 1. So we know that Brownian motion is invariant for KPZ, well, invariant up to height shifts. Okay, or the derivative of Brownian motion, white noise, is invariant for stochastic Burgers. We know that because why? Because we have discrete models like asymmetric exclusion, which we know in the weakly asymmetric limit, it goes to KPZ, and we know its invariant measure is Bernoulli. So of course, that's a proof. So the proof exists, but the question was always bothering me for many years. Can we do a direct proof of this thing, right? And semi-direct proofs exist. So for example, Perkowski and Gubinelli, they have actually been able to write down a generator for the KPZ equation, and that thing you can show that certain things are martingales, and so okay, the Brownian motion is invariant up to height shifts, but the proof is actually not in there. It actually just come again from discrete models. Okay, so there's actually no proof in there, but here's the direct proof. So the direct proof, you just apply the formula. Okay, we'll take U0 to be, you take a spatial white noise, and now I'll just convolve it again with some other smoothing kernel. And now, if you calculate this other term, the last term, you can just recalculate this by integration by parts. This is just a standard Gaussian integration by parts, so I won't go through it. It's the same integration by parts like I did before. You just throw the Malliman derivative on the other side, but then there's no twist like in the previous thing. It's just direct thing. And you find out that it just gives this term, which is exactly the missing, it just cancels this. They just cancel each other. You're just left with this. You just have that. And Stein says that tells you that y is Gaussian. That's the end. Okay, so the magic cancellation, this crazy mystery, why on earth does KPZ preserve Brownian motions? You know, KPZ without the nonlinearity preserve Brownian motion, and then you put in this nonlinearity to still preserve Brownian motion. That's completely amazing. But it's all actually, at least in this story, because of this amazing fact that when you do Ito, this term just, poof, drops out. Okay. All right? That's application 1. Wow, I'm talking a bit fast. When did we start? 2:50? Okay. All right. So lots of time for questions. Application 2. Okay, so this I'll have to go a little bit slower. Okay. So now I want to look at point-to-line polymers. Okay. So point-to-line polymer just means, well, you can just think. Maybe you want to think about directed last passage percolation. And you have last passage in some environment. And now you just do point-to-line, which means the thing is just allowed to go anywhere. Okay? And those are the polymer paths. But I want to do it in the asymptotic limit. Okay? Now, in this setting, we can start at x1 and x2, and you have these polymer paths. They're going at time t to this line. Okay? Or by the way, you can think of the KPZ polymers right now too, but I'll pass from there in a second. Okay. Now, you start one at x1 and you start one at x2, and then you do this thing with a horizon of time t, just like I was doing in the previous thing, these polymers. And then you can ask the question, did they coalesce or did they not coalesce up to time t? Well, did they or did they? There's some probability that they did one or the other. Okay. Now, just for the sake of having formulas which are tractable, I want to go to the asymptotic world, do the 1, 2, 3 scaling on the KPZ equation to go to the KPZ fixed point. Okay? The formula, which I showed you, is completely invariant under 1, 2, 3 scaling. So exactly the same formula is true for the KPZ fixed point. So now at the KPZ fixed point level, the positions of the polymers at time t are just actually the argmax over y of the KPZ fixed point at time t, position y, starting from a narrow wedge at x. Okay? That thing has a name. That's the Airy sheet. So the Airy sheet is just the fundamental solution of the KPZ fixed point starting from a narrow wedge. If you don't know what a narrow wedge is, it just means 0 at the point x and minus infinity everywhere else. And that thing blows up into a parabolic thing with fluctuations on top, which is called the Airy sheet. Okay, so that's the Airy sheet. I hope if you don't follow the notation, just ask me. It's actually at the bottom of the page too. Okay, so in my notation, the KPZ fixed point, it's a time-dependent process of functions of y, and this is the initial condition after the colon. Okay. So these things just go to the argmax because the whole thing is just optimizing the whole time. And because of this picture, you can just equivalent say the question is whether the argmax is starting at x1 is the same as the argmax starting at x2. It's just another way to say the same thing. Okay. I want to mention that there are other models of polymer coalescence, and I'll talk about them. This is a particular one. Okay. Okay. So we asked what the probability that tau, say 0x, the thing's homogeneous in space, so we might as well start at 0 and x, is less than or equal to t. And because of the invariant scaling of the KPZ fixed point, this is actually just a function of x over t to the 2/3. So there's some function rho, and it's some universal function. And the question is there a formula for this function? And that was asked to me by Derrida. In fact, the way it worked is hi, the first time I ever met him, hi, I'm Derrida. Can you find a formula for the, exactly like that. And then I told that to Yugu, and he said, really? And then he showed me email from Derrida about 8 years after he had asked me. It said, can you find a formula for this? It's exactly the same thing. Okay, so is there a formula for rho? And yeah, and the answer, well, here is yes. Yes, I'll show you the formula. Okay, so you take, so we're going to take h0 equals 0 in our formula. That corresponds to this fact that it's point to line. Okay, so you're not getting any reward at the end, and that's a particular choice here. And we'll take f of y equals y. Okay, and then I'll keep in this little f function. And then you find out that this is just our formula written in this special case. Okay, but you see what happens if you look at the sign of x2 minus x1 minus its initial sign. Again, you have this same business that once they come together, the sign, it's just 0 once they come together. So this is either 0 minus what it was initially if they came together, or just 0 if they didn't come together, right? So obviously, if you, using this thing, you can compute this probability, right? So the probabilities are hiding inside the formula. So okay, you just undo the thing a little bit. You find out that rho x is the derivative in space of the KPZ fixed point at time 1 from 0 to x squared, starting from initial data 0. Okay, that's called the ARI1 process. And the main thing is, well, we have exact formula for this, right? We know exactly the joint distribution of h10 and h1x. In this case, it's just some Fredholm determinant. So okay, I'll write it on the next page. I said I won't write it, but I will on the next page. There's an exact formula for rho x, and here it is. Okay, the formula is not pretty. None of them are. Okay, so the probability that tau 0x is less than or equal to 1 is just 2 integrations of a determinant times essentially its derivative. The k is I minus a projector. Okay, proj means projection onto that space. This is the heat kernel. This looks like the heat kernel backwards, and I'm not allowed to write it, but this times this is an explicit kernel, a completely explicit kernel, and this is the reflection operator. Okay, well, it's a formula. And these functions are just some funny function that would come out of this calculation, and I think you see whenever the heat equation written backwards, it's followed by a minus I d cubed, which is a bunch of area functions, and this is totally legal. This is an explicit integral kernel, which I'm just not writing for your sanity. Okay? Fine? Okay, so that's the formula. And see, one of the reasons this is interesting, actually, I'll go back for a sec. We have formulas for the KPZ fixed point. You start from any initial function. You know the joint distributions at a fixed time t in all y's of this ht. That's the KPZ fixed point formulas. Okay? But this is not something which is contained in there, knowing what's the distribution of this, whether these two argmaxes are equal. That's not there. This is the new information we're getting. Okay. All right. Now, if you look at asymptotics of this thing, so of course the natural question to ask is, well, what happens when x is small or when it's huge? What does it look like, right? And if you look at asymptotics as epsilon goes to 0, well, Duncan, my colleague, he already worked that out with his soft methods. And so as epsilon goes to 0, it's epsilon over the expected value at time 1 of one of these polymers, plus some term of order epsilon squared, which is correspond to whether there's 3 polymers starting in this. Okay, et cetera. He has an expansion like this. Okay, it's not written down, but he promises me he could prove this. Okay, and we can start doing asymptotic on our exact formula, but actually, even at the level of trying to prove this, we find out that it's one crazy determinant over another crazy determinant. As I said, this is a work in progress, and presumably we'll be able to get his expansion out of our thing. Okay. Okay. And then for a slightly different version of the problem, so we have an inverse gamma polymer, and now these guys, Firaz and Timo and Hashan, they're looking at a slightly different problem. So they sort of pull the thing back to minus infinity. So in my language, this is a directed infinite horizon problem, okay, as opposed to ours, which is, you see, there's an important thing here. This is a finite horizon. I only made the polymers go up to time t, and there are only those polymers in that interval 0 to t, and then I asked whether they merge to time t. Whereas what you guys are doing, you have infinite time horizon, and okay, slightly different model. And then they can prove that, so this is what they prove in our language is tau 0x as x gets large looks like e to the minus some constant times x cubed. Okay, that's what it is in our language. Okay, so it's large x. And then, in our case, actually, the probability that tau 0x is less than 1 is just the derivative of the covariance of the ARE1 process. And we got a bit lucky because these guys already did the computation for us. So Bazou, Buzani, and Ferrari already computed that the covariance of the ARE1 process is e to the minus 4/3 x cubed. So your constant's 4/3. Okay? You can check it is anyway, right? You know that, right? You can check that it should be 4/3, yeah. Okay. Now, the thing that corresponds to their model is actually not to have 0 initial condition, but to have Brownian initial conditions. Okay, that's sort of the equilibrium version of this whole thing. And for the Brownian initial condition, our formula gives something really weird. So for the Brownian initial condition, what it does is says, I'll give you a formula, but you have to take an extra derivative in the variance of the initial Brownian motion. Okay? And this one is a little different than the others because I don't have an exact formula for the KPZ fixed point starting from a Brownian motion of variance nu. Okay? There is an exact formula if you start with variance 1, but I need the derivative. Okay, so far this is another, as I said, it's a work in progress. So okay, this is a formula, but it's not a very useful formula yet. So getting a useful version of this like this is one thing we're trying to do. Okay, good. Okay, next. So now when you have a coalescing system like this, well, you see, if you're in some interval, they either coalesce or they don't, and you make it wider and wider and wider, and then certainly you get to a point and they don't coalesce, right? So those points between which everybody is coalescing up to time 1, and then it stops, and then they start coalescing to each other in the next interval. Those are points, and that makes a point field here, right? So that has a name. It's called the LPP lower point field. Okay? So another way to think of it is that if you take the argmax in y of the area sheet, now that's a function of x, and this is a piecewise constant function. It has jumps exactly where these points are, okay? So now we'd like to get a formula for this lower point field. Okay, so what do? I'm not gonna, I'll just tell you in words how you get the formula. So you do roughly the same thing as on the previous slide, except you keep doing Gaussian integration by parts over and over and over with, again, the same thing every time you get one of these horrible terms that Gerard was mentioning, you notice that the stochastic integral vanishes. And you keep throwing it away, and you keep doing. So you do this k times, and you get the following formula. So you calculate that the probability that if you have a bunch of unions of intervals is empty is just some double factorial constant times. Okay, so you have derivatives at the odd ends, at the ends of the intervals. So these, you see, these are non-overlapping intervals, and they take the derivative at the odd guys. Okay, and you keep taking derivatives, so you have k derivatives for 2k points of the, and this is just the area 1 process square increments along your whole process. Okay, again, we have an exact formula for the multidimensional distributions of this process. And so this is just a sort of how many 2k dimensional integral of a huge Fredholm determinant, and then you take all these derivatives and you get a formula. Okay, so there's a formula. So the thing has a formula. Now, there's an interesting question. Is this process actually a determinantal point process? I don't know. We only just got the formula, and the formula, of course, has many determinants in it. It's a horrible mess because you took k derivatives of a Fredholm determinant, integrated it many, many times. But well, okay, maybe it is, maybe it isn't. Okay, but you see, this is the whole story, right? Because once you have the emptiness probabilities of a point process, unless the points can overlap, which they don't here, then it determines your whole point process. So this completely determines the point process. Okay. How much time do I have? No, I don't have 10 minutes. If I have 10 minutes, I'm going to finish early. Okay, so here's our failure. I'm going to tell you what we really want to do and have not been able to do yet. Okay, so this is in a sense our real goal. Okay. So you take the KPZ equation, but now you have smoothed out noise. Okay, so here, now that C, it actually has some covariance in space. Okay, now this guy is known to have an invariant measure. So it's known, so there's a work of Dunlap, Rizek, etc., who proved that the stochastic Burgers with this with this kind of noise does have an invariant measure. Okay. But the thing is, we have no idea what's this invariant measure. Nothing. Zero. You think, oh, the thing must be something like Brownian motion, but we have nothing like that. No information at all. And everybody think, oh, this whole KPZ universality class, the whole problem is solved. We have absolutely no idea how to prove that the KPZ equation with smoothed out noise is in the KPZ universality class, converges to the KPZ fixed point. Not even for any initial data, nothing. There's just absolutely no result. There's no approximating microscopic model that is useful in any sense. Nobody knows anything. Okay, so if you use our formula, or at least the steps to our formula, you get an equation like this. Okay, how do you get this equation? So this is just the equation I got by integrating by parts in the first page, except now you no longer have that this stochastic integral goes to 0. It's just there. And but wait, you did it up to time t. You just did it on interval 0 to t. But now I can take t to infinity because this thing only sees the integration from sigma to tau from the first, and we sort of know that must be fine, right? So you take t to infinity. You started, by the way, sorry, I should have said, you believe that the thing should just be something like, the thing, meaning the invariant measure, should be something like the Gaussian with covariance R, right? That's your guess. So you start with that, and that killed one of the terms in the original expression. And that's how I got this expression, okay? And then I sent t to infinity to get the invariant measure, okay? So this is an exact formula for the correlations of the u in the invariant measure in terms of whatever this thing is. But the problem is, how do you show that's finite? Sorry? Sigma is the first time that the two polymers got into the range of R. Let's think of the R as just having range 1. Just think of it as a box of range 1, okay? So then it's the hitting time of x1 minus x2 of 1 or minus 1, depending on where you started, okay? Actually, you can rephrase the thing a little bit better. Suppose I just want to know the simplest thing about this invariant measure, that it has like, fluctuation of size root L, right? So you just want to know that in the invariant measure, HL minus H0 squared, that this thing should be about L. So this thing should be bounded or something like that. That's the kind of thing one dreams. Okay, if you can prove this, you believe you might be slightly along the way to trying to prove KPZ universality for this model. Okay, that thing, now I just took this thing and I integrated by parts again. Okay, it's just it's just the average of this polymer measure from 0 to x. So x is what's being averaged. The two polymers start at 0 and x. And then R prime, well, okay, R prime. So just take the thing, don't make it not be a box, make it be a triangle. So R prime is just constant little box, okay? So you're just asking how much time the two polymers spend within distance 1 before they hit each other and then everything disappears. But see, the problem is that I didn't start with the invariant measure. I started with my approximation of the invariant measure, which is this Gaussian with covariance R. And so the whole problem is non-stationary. And since the problem's non-stationary, you just have no, okay, we're a bit stuck right now. We don't know how to bound this term. It should be bounded, but okay. So I must stop.